Welcome! In this video, we're diving into the design of control units, focusing on how finite state machines, or FSMs, are used to manage digital systems. We will explore the key concepts of finite state machines, understand how control signals are generated, and look at the process of sequential logic design. So, what exactly is a control unit? Simply put, it's a digital circuit that generates control signals. These signals are essential because they coordinate the operations of all the other components within a digital system. Think of it as the brain of the system, directing traffic and ensuring everything runs smoothly. A basic structure of a control unit takes inputs, processes them in the control unit, and generates corresponding control signals. Now let's discuss finite state machines, or FSMs. An FSM is a mathematical model of computation used to design control units. Key components of FSMs include states, which represent different conditions or modes of operation; inputs, which are the signals that trigger transitions between states; outputs, which are the actions the FSM performs; and transitions, which define how the FSM moves from one state to another based on the inputs it receives. A simple FSM is shown with two states, namely S0 and S1. There are two main types of FSMs, Moore and Mealy. In a Moore FSM, the output depends only on the current state. This means the output is stable for a given state, but it might be a bit slower to respond to inputs, typically with a 1 clock cycle delay. On the other hand, in a Mealy FSM, the output depends on both the current state and the input. This allows for faster responses, as the output can change immediately with the input. However, it can also lead to more complex designs and potential timing issues. Thus, Moore FSM's output depends on current state only with slower response time. Mealy FSM's output depends on the current state plus input, with faster response time. Designing an FSM-based control unit involves several key steps. First, you need to clearly define the problem and the requirements. What should the control unit do, and what are its constraints? Next, you identify the different states the system can be in and the transitions between these states. Then, you create a state diagram to visually represent the states and transitions. Finally, you build a state table, which is a tabular representation of the state diagram, showing the next state and outputs for each current state and input combination. Thus, the design flow goes from problem analysis to state identification and finally to implementation. Implementing a control unit involves several key elements. There's the state register, which stores the current state of the FSM. Then, there's the next state logic, which is a combinational circuit that determines the next state based on the current state and inputs. Finally, there's the output logic, which generates the control signals based on the current state. Shown here is a Python example showing a class called control unit. The class shows initializing the state to idle, and then a method called nextState to determine the next state of the system. Key elements include state register that stores the current state, next state logic, which is a combinational circuit, and output logic that generates control signals. Control signals are the heart of a control unit, directing the operations of other components. These signals can be categorized based on their function, such as memory control signals like read enable, write enable, and chip select. ALU control signals, such as operation select, enable, and flags. And register control signals, such as load enable, clear, and clock enable. An example timing diagram is shown with clock, enable, and output signals. Control units are found in a wide range of real-world applications. Microprocessors and CPUs, gaming controllers, industrial automation systems, automotive systems, and many other digital devices rely on control units to manage their operations. Some of the key takeaways are that FSMs provide structured control logic design. There are Moore versus Mealy trade-offs in timing. Systematic design process ensures reliability. In conclusion, control units are the brain of digital systems. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.